Hello, my name is Lim Ping Guan. Today I'm going to show you my live execution process for Lab 2. Let's look at question 1, where we initialize two 16-bit variable, which the var1 is set to 1 and var2 is set to decimal 9. To get started, I have set a breakpoint on our first line of code and press F5 to launch the debugger, and here is the register content. Now I will press the F10 line by line to execute my code. So the first line is move AX var1. This copies the value of var1, which is 1 and in decimal, and to the register AX. As I press the F10, the register AX changed to 0001 in hexadecimal, which is the value of var1. And next is line 2, move BX var2. This move the value of var2, which is 9 in decimal, to the BX register. After I press F10, the content of the BX register changed to 0009 in hexadecimal, which is the value of BX. So now is the main operation on the line 3. So we exchange the AX register and BX register content. So after I press the F10, the AX register and BX register is swapped. The AX register now changed to 0009 and BX register changed to 0001. And the final two line here, line 4 and line 5, just take the new swap values from our register and commit them into system memory. Moving on to question 2, we are evaluating a 32-bit sign expression. R val equal to negative x val plus bracket y val minus z val plus 1. Our input are x val 26, y val 30, and z val 40. And R val is uninitialized right now. And I've also set my breakpoint on line 1 and press F5 to start. Now I press the F10 line by line to execute the code. Our first code is move EAX x val. So this will move the value of x val 26 to EAX. So after I press the F10, the EAX value changed to 001A. And the line 2 is negate EAX. This instruction negates the value inside the EAX. After I press F10, the content of EAX changed to FFFF FFE6H. This shows how the processor show a sign negative 26 using 2's complement. Now it's line 3. Move EBX Y val, which move the 30, which is the value of Y val, into EBX register. So the EBX register changed to 0000001E in hexadecimal. And line 4 is sub EBX Z val. We subtract the 40 from 30, which is the value of EBX from value of Z val. So the result will be negative 10. After I press the F10, the EBX value changed to negative 10, which is FFFF6 in hexadecimal. And line 5 is add EAX, EBX. This adds the two results of the register together. So after I press F10, the EAX changed to FFFF FFDC in hexadecimal, which is negative 36. And finally, the line 6 is increment EAX, which add one of the EAX register. And I press F10 again on the last time, and EAX update to FFFF FFDD in hexadecimal, which increased by 1. So our final answer will be negative 35. So this 35 will undergo line 7, which will just commit this back to the system memory. So that's all for question 2. Let's stop the debugger and move to question 3. Now for question 3, we are evaluating an unsigned 32-bit expression. var4 equal to var1 times var2 plus var3, and this value minus 1. Our input variable are var1 5, var2 10, var3 20, and var4 is uninitialized. And I've set a breakpoint on our first line and press F5 to launch the debugger. So now I will press F10 line by line to execute the code. Line 1 is move EAX var1. This will copy the value of var1, which is 5 in decimal, into EAX register. So after I press F10, the EAX register will change to 00000005. And line 2 multiply var2. This multiply EAX by var2. After I press the F10, the EAX will multiply by var2, which is 00000032. And line 3, add EAX var3. This add 20 to the EAX register, while the var3 is equal to 20. And after I press the F10, the EAX register changes to 000000046. And finally is line 4, which is the decrement EAX, which subtract by the EAX register by 1. So I hit the F10 right now, and the EAX register will increase by 1. And that's a successful run for question 3. And I will stop the debugger and move to question 4. Let's look at question 4, where we process a 16-bit word operation. Our input are var1 equal to 40 and var2 equal to 10. And the operation is var1 times 5 divided by var2 minus 3. I've set a breakpoint and press F5 to open the register panel. So let's step through using F10. Line 1 is move AX var1. So after I click the F10, the AX register will change to the value of var1, which is 0028 in hexadecimal. And line 2 also, same with line 1, we store the value of 5 to BX register. So after I click F10, the BX register will change to value of 5 in hexadecimal. And line 3 multiply BX. So which multiplies the 40 times 5 equal to 200. So when I press the F10, the 32-bit result is split across the DX AX. So AX update to 00C8 and DX update to 0000 because there's no overflow. So line 4 and line 5 is the calculation of our divisor. So line 4 is we store the value of var2 to dx. So dx will be value of var2 0008. And line 5 is subtract the bx by 3. So the bx will be subtracted by 3. This is 10007. And now is the division of line 6. Divide bx. So this divides our 32-bit dx ax value by bx. So which is 200 divided by 7. And I will hit the F10 right now, and we got the quotient, which is ax 001c, and our remainder, which is dx 0004. And the last line is line 7, move var for ax. So just save our final quotient back to the memory. Okay, so that's all for the line 4, question 4, and we move to question 5. For question 5, we are testing a multiplication overflow layout. I've removed all the breakpoint and pressed Ctrl plus F5 to run the code natively, so the dump register instruction can print this black console window. Here we are multiplying 1000 hexadecimal by 25 hexadecimal. Mathematically, that equals 25000 hexadecimal. Since this is a 20-bit value, this exceeds the 16-bit storage limit of a single word register. Let's look at the console snapshot. EAX shows its lower 16 bits as 5000 hexadecimal. EDX shows 0002 hexadecimal. Reading the DX-AX pair together gives us product 0002 5000, which is the DX-AX pair together. Because DX is active and non-zero, the processor signals an overflow. So if you look at the flag listed at the bottom, CF equal to 1 and OF equal to 1. So this proves that the arithmetic overflow occur. Okay, so that's all for the question 5. Let's look at question 6, which shows an 8-bit division using divide BL. I've run the code using Ctrl F5 to check the dump register. Here we divide the 803 by 10, leaving a quotient of 128 and a remainder of 3. So the remainder will goes to AH and the quotient goes to AL. So looking at the dump register, the EDX completely stay at 0000 hexadecimal. This is because the 8-bit division completely ignore DX and use strictly the 16-bit register AX as the dividend. So in 8-bit division, the remainder goes to AH and quotient goes to AL. Looking at EAX, it only read the value 000380 hexadecimal. This means that the AH hold 03 hexadecimal and AL hold 60 hexadecimal, which equal to 128 in decimal. So that's complete of my full demonstration of Lab 2. Thank you very much for watching.